Hello, welcome to Point One Studio. My name is Jungwoo Park. Today, I'm going to continue the world analytical model from last video by using Revit and SOFiSTiK. Especially, we'll look at more details such as wall connections in horizontal level and also vertical levels. And we can also take a look at more detailed parts between the different wall profiles, and also maybe we can also look at the joint between columns and wall. This analytical model in Revit applies not only for the SOFiSTiK, but also it applies for robot structural analysis or Dulber's RFEM and any other FEA analysis package. So I think it could be very interesting for structural engineer or architects who use calculation software. And unfortunately we don't have like option to use analytical model with angled wall in Revit. This thema I'll cover next time in the following video for the next part. Maybe we can come up with some different workflow to create analytical model for angled walls. Anyhow, today we have a lot of interesting case studies for the walls, and I'm going to make this series every week from wall to floor to columns and framing structures. So if you have any wish to know more about analytical models in Revit, please feel free to leave the comments below. And if you missed the video from first part, please look at the link above and you can find out the video from last time. So alright, then let's get started. So from previous examples, I'm continuing this time all these wall parts. Let's look at this curved wall, for instance. And we have already set up the analytical mode wall and our support condition. I'm gonna look at, for instance, this part where we select curved wall, and I'm going to make a section box on it. Let's take a look at the analytical surface. As you see, I was explaining about this all alignments from the last video, and we have the same material. So I'm going to look at SOFiSTiK now. Let me pop up the structural property window of the SOFiSTiK, and when you select the analytical model, we can have a look here, the mass density and etc. But for now, I'm just going to use the same settings from Revit, and let's go ahead, click on the SOFiSTiK analysis, and I'm gonna, at the moment I didn't assign any load case, but we'll use dead load for the self weight. Right, so everything is good. I'm just calculate. And it's good to go now for SOFiSTiK system. Right, so we have now the curved wall structure. It's, as you can see, I'm visualizing in SOFiSTiK now to just see the sections without thickness, and the mesh geometry looks good for me. And we could maybe calculate now the linear analysis. Alright, the calculation is done, so you can have a look now the deformed geometry, and I'm gonna turn on the wall here. As you can see, when you have curved wall, because it's FEA analysis, it will divide like certain division for your chord mesh geometry, and it will get quadrate like rectangle quadrated mesh geometry. So this is how you can see the result. And of course, if you double click on each mesh in SOFiSTiK, you can see the mesh node numbers, and accordingly you can see at this node you can see all the deformation or physical utilization information from the this property window. Alright, I'm going back to Revit, and this is fine, it's nothing complicated. And what if I go next step now? We can probably, I'll go forward here from the example. And what if we have openings on curved wall? Because curved wall, we cannot just insert a generic. I think we could insert generic model for sure, but we cannot just modify the profile to create the opening. So what I did in here, I created simple Revit model in place by creating wall, and I gave the option with void form extrusion to create openings. So I can show you here if I select the correct family. Let's see on the families, and we can go to wall, and here I made a name called void, and we can edit. Okay, I can make it select from this view, and I can make it edit. So if you see here, I create void extrusion as a wall family in place, and I just used cut geometry operation to create openings here. And of course here I just create this also wall end. If you look at in the plan for this wall, particular wall here, I created this sort of cut at wall ends, and I wanted to see how the analytical model going to be look like. So the result here, I'm gonna cancel. Result here is we just cut out the physical wall, curved wall, and accordingly your analytical model is also updated. Of course here when you adopt the analytical model with opening, you can also you can close in Revit or open it. This all detail we already talked about last time, and now I'm just going to go ahead to calculate in SOFiSTiK. So let's go ahead in SOFiSTiK, and here what is going on with SOFiSTiK, I'll just close. Okay, now it works back to physical, and I'm going to start recalculate this view, and I can open the SSD now from here directly. So you can see yeah, the mesh is a bit more dense because of the opening, and you can see there we have different geometry in SOFiSTiK, which is great. And I can calculate, of course, but what I'm gonna do, I'm gonna select the wall here, and I can perhaps here mass density we gave right now as a default density, which follow when you start calculate. We can see here on the meshing, and it will determine automatically this massing density. But I want to give here particularly here, let's say we want to create by 20 centimeter of mass density, and let's have a look now. I'm gonna calculate it again. So just keep in mind this is the current mesh from automatic generation, and I'm going to create now one more time with a 20 centimeters of massing density. And when you look at the result in SSD, it looks like more or less same. Perhaps let's create a bit more. I'll make it just exaggerate to make it a bit like 5 centimeter, and I'm gonna calculate once more. Let's see what's changed. The calculation takes a little bit more time, and now in SSD, as you can see, the mesh is really dense. So if I calculate, of course, now the linear analysis, because of the meshing is more dense than before, the calculation time takes more, but it's just very quick in SOFiSTiK. And as you can see, we can have a look more detailed analysis from this meshing geometry. What I'll do, this result, remember we could also show the result in our current view with SOFiSTiK, and what I need is wall result. And you can see in Revit we could find out, of course we have also here the legend, color legend, and you can find out different analysis result in Revit, which is great because which means you can create the diagram, or you can put this in your sheet, drawing sheet, and you can display this Revit graphics with this SOFiSTiK result. All right, let's move on. So I'm gonna disable the this view for SOFiSTiK, and now let's move on to another example here. Now we have here in Revit with structural wall, and also we have wall foundation, and which foundation is enable the analytical model. So if I temporarily hide my physical model, you might see here analytical wall foundation, which is linked. And what I'll do, I'm gonna delete this boundary condition and leave wall foundation as a support, because it's supposed to be support, and it will analyze as foundation. But let's see how it works. So I'm going to start calculate current view, and I'm assuming maybe the calculation might fail from this view. Unfortunately, the geometry is not came. It's funny. I'll try one more time. Calculate. Yes, finally. Yeah, I'll make zoom 3D view. Okay, here we go. We have the view. As you can see, even though we use foundation as analytical model, the thing is we don't have support condition on bottom of the wall, which is maybe this is depends on your FEA calculation third-party software, but at least for the SOFiSTiK it doesn't come. So when I calculate the whole structure, you can clearly see there's no support from the bottom of the wall. So you see all the stresses happening on the side where all the fixed supports are, which is a bit funny. So just keep in mind that in Revit, when you use just support condition, then just the foundation, then it doesn't give you actually support condition of the wall. So you still need boundary condition you have to place. Here I put custom boundary condition, which has fixed condition on NX and Z translations, and Y translation is released, and there is also rotation of X axis rotation. And if I now turn on the physical view and foundation, perhaps I'll also disable the analytical model, because delete specified element. Okay, it's funny, you know what? Because the boundary condition was assigned to the analytical model of foundation, not to the wall. So that's the reason why when I disable the analytical model, that boundary condition is automatically deleted. So for now, I'll just leave it, because it doesn't matter for me to calculate. As long as we have boundary condition on the bottom of the wall, it will calculate for the wall calculation. So let's try. I'm gonna start calculate. Now if you look at the result, as you can see, we have that boundary condition, and let's calculate in analysis, linear analysis. Then we have here the result that we was imagining from SOFiSTiK. That's great. All right, so let's move on to, so what is important here, if you use wall foundation or foundation family in Revit, you can enable analytical model, but it doesn't work as a boundary condition. So you may have to put boundary condition in using Revit in order to calculate correctly for your boundary condition. All right, now in the wall, now let's look at some wall condition. Here I have two wall 90 degrees joined each other with a butt joint option. So when you look at the plan, here they have the butt joint. If you want to modify your wall connections, on the modify you have here wall joins option, and when you highlight here you can choose between butt joint, miter joint, or square off joint connection. And here I just made the option to don't clean join. If you clean join, then you don't see the joint area, but I just want to don't clean the joint to demonstrate this analytical model. And that's how you can control different wall joint in Revit. And according to your joint condition, of course, analytical surface also, wall surface also join, but at the moment they are auto joint, which means I want to here give filter. Last time in the first video, remember I create this another filter for node connected, adjusted, manually adjusted, or wall not joint is not connected, and I'm going to use the same filter here. So for unconnected one, I'm going to give a red color, and node connected, automatically connected, I'm going to give sort of green color, and if we manually adjust, I'll give this blue color. And let's have a look now. So you can see the node points on wall edge, because there is no connection. Of course, it shows red, but the wall between them in this joint area, the node is auto connected, which is good. So now I'm gonna calculate in SOFiSTiK to see how this structure behave, and I'm just gonna calculate. And when you look at SSD, now we have by the way, in here when you click on 3D view, it just zoom into your current model. And now if I calculate the linear analysis, and you will see the dead road, and it works. It's like it's moving in z-axis, right? All right, that's interesting. Now I'm going back to Revit, and let's go to next example. Here we have another example. You might model your Revit wall by using, you see here we may have this butt joint, but perhaps let me go back to plan. Here in this case, you see here a small symbol, which means we disallowed wall join. So sometimes we can make it join, then they are joining, or you can make this node point, you can hit mouse right button, and when you disallow join, you can push it back. Sorry, you can let me use align, and as you can see, you can make butt joint, and you're not allowing automatic joining between the wall. But in this case, you might have. I like this solution if it meant to be, because when you export to IFC model in Revit, this gives you the best result. But nevertheless, the the analytical model, they are not joining, as you can see. So what we can do, if we export now just without any settings, let's calculate. Then of course your calculation model, these walls behave as a separate object. That's what I was assuming. As you can see here, when you give thickness, you can see there looks like wall together, but when you hide the thickness of the wall, actually these two are separated walls. So if I calculate the dead road, you may see here they behaving sort of looks like a little bit separate, behave separately, like individually, I think. No, actually they are. What it's interesting, because I was imagining they are going to work separate wall, but actually SOFiSTiK seems like they are. Let me see the mesh. No, it is separate. Just the no, it's not completely separate. You know what? Because they are deforming together. Although the mesh join is not 100% join each other. So what I'll do, I'll make a small test. Let me isolate only this one side of wall with analytical model, and let me calculate again for this one here. Calculate, and when you look at this here, now it's individual wall, and I'm gonna calculate analyze, linear analysis, and if you look at the, yeah, okay, so that's how that road behaves. So it is actually, the previous analysis was actually separated wall. They are not connected each other. So what I can do here in this case to connect them, you can press tab button in your keyboard to select your analytical module, and here we have analytical adjust. So this, what it does, we can adjust the wall end by clicking on wall adjustment, and you can see on bottom left here, pick analytical wall for adjustment. I want to adjust this wall, and then it shows pick target analytical model. I want to target this analytical model here. In this case, then it joined like it, you know, it's not perpendicularly joining there, which is bad. So I'm gonna undo. Let me do this edge here on this horizontal boundary, then it just joined there, as you can see. And let me try again that one. I want to so I'll pick up there and target, sorry, one more time here, and target. I cannot target them anymore because it's joined. Let me wall adjustment. This one I cannot target anymore. So this is like a bit tricky in this case, because you see it joined here, and then you might see the edge of the result there. But what we can do, we cannot move the node point. Yeah, there is no way we can split and delete this analytical surface in Revit for now. So I leave it, and then we can calculate. And you might see now the meshes, they are joining together, as you can see, very clearly join each other. And yeah, but we still have this wall end is coming out, so which is a little bit bad. Let's calculate to see the result. And if you see now the dead road result, they actually behaving together, not individually. But because of the join, the extra piece here, this is something that we want to have it in Revit. So I guess this solution is not good if you model wall, you know, if you dissolve join at the end of the wall. This result is not very good for the calculation in Revit. Let me undo. Sorry. Undo this join. I'll leave it as it is, and perhaps I have another idea. Let's change this one to there first of all, and then when you do next wall here, this one targeting to it doesn't let me target anymore. This is strange. Let me finish and select analytical adjustment. I want to do this one to, yeah, it doesn't let me connect anymore, which is really annoying. Even if I use a line, doesn't let me. So this target, I cannot target anymore. So in this case, what I did, the kind of the edge, the wall end which goes extended part, I just shrink, like reduce to here. And in SOFiSTiK we have another option. We can use, when you calculate here on the geometry, we can give the tolerance for intersection of structural element. So we can use, like, let's say I want to give 1 meter. If any element has gap, like more like it's like up to 1 meter, I can join them automatically. So let me calculate. So the SOFiSTiK is intelligent enough to calculate this sort of gap, and it's as you can see here, we have joined, perfectly joined wall structure. So if I calculate this, you can see in here on the dead road, they are behaving together. This is awesome, really nice. That's something that I wanted to see. And if we don't use SOFiSTiK's automation tolerance option, what we can do also is that the analytical model, and we can give analytical link. So link is something that we can link between the node, and in this case the bottom link, we can give the link, and this link we can give the some sort of connection settings. So this link means actually it's just it's kind of coupling. So when you click on the link, it's coupling between the analytical world end. But what is not good is that this is only connecting node to node in Revit. You cannot, there's still this connection between the points. For example, here in the middle or any edge of the wall here, they are not joined each other. So when I calculate this one now, let's calculate. I'm not gonna join, I'll use relative 1 centimeter tolerance. And when I calculate it now, in SOFiSTiK we will have a coupling. You see here we have this coupling link. So eventually when I calculate the analytical analysis for this wall connection, you may see now in that road they are connected, but in between here it's difficult to imagine in the realistic case. So this is not very good solution for wall. Perhaps this is good for between the framing structure, but we'll talk about more detail in the next videos. So in this exercise is not very good for the wall joint. Just keep in mind that perhaps using this disallow join option is not good for the structural analytical model of the wall. Next, so I think that's clear. Let's move on to next. And here when you have a miter joint, this is miter joint of the wall joint, and you see the structural analytical wall surface joint automatically very clean. So we'll get the more or less same result as the butt joint. Let's have a look at the analytical model. So you can see here we have the mesh and they are joining together clearly. So this is good. So miter joint is not a problem to work with analytical surface. And when you see here square off joint, which means here we have here ends finished. Let me go to the plan. And if you look at here, we have square off joint. And because of the analytical surface is going to the middle of the wall, and they just joining together at the intersection here. So when I calculate, they will have same result. I mean the result what we expect to. Well, let's calculate it, and if we can have a look. The mesh, and as you can see, we have the behave like meshing geometry that we expected to. So this is good. So these wall joints are not a big problem. And let's go to next situation here. So in this situation, I'm just showing you another level, but the gap, there's a gap that we actually wanted to connect, but somehow for some reason with architectural detail, maybe there need to be the structural wall here need to be separate, but we want to calculate them as a structure. Then what we can do here, and we can analytical adjustment for the wall. So this wall joint we can connect to this end, and here another this joint we can connect to here. So we have like a complete joined wall analytical surface. But as you can see, what we have to be careful about it is that the opening also changed. So I don't know if this is big deal for structural engineer, but this you can see because of the extended wall adjustment. So this opening also a bit changed. There is nothing I can do for that. I cannot, you know, stretch this wall surface node points, unfortunately. So just be careful for this part when you manually adjust your wall ends up towards this another wall connection. It'll work, but your opening may change. So let me calculate this one now. It's interesting case study for the wall connections. And when you look at the here, the meshing geometry, these are all joined clearly, as you can see. That's very nice. And I want to calculate this time. What is nice also here, this we changed the profile of the wall, and all the meshes works perfectly together between the level. And now if I do linear analysis, we will have dead load from the self-weight, and you can see we can get the whole structure analysis of the whole structure, which is nice. And this data again we can always display in our in Revit view, which is super nice to see. Look at the force here, which is nice. Surface of this result here, if I do here, yeah, that's very nice. Alright, so let's move on. Now I'm gonna move on to next wall joint situation here. Yeah, in this case we have a little bit of different joint, and if I hide physical model, as you can see, between the level they are joined correctly, and yeah, the automatic join connection is all good. So I think this is good to go for the calculation. Let me calculate. And when I do look at the mesh here, all wall joint looks quite good. Yeah, as you can see, this is like something that I wish to see. And when I analyze now on the dead load, you can see deformed geometry here. Yeah, it's very logical because here we have more wall mass above, so you can see the deformed geometry is slanting towards this direction because the self weight here is heavier, and so we have more force from there, which is really good. I mean, I'm not structural engineer, I'm an architect, but it's really nice to see this sort of analysis when you design architectural design. And I think we should always work together, really. This you know, we know, of course, obviously it's very logical, but I think computer tools really help you to make a good design, and also for the collaboration is really nice. Let's move on. Next case. So same, we have curved wall, and then here on the bottom we have joined here, straight wall is joined to the curved wall, and above we have another one, but which is cantilevered a bit here. And if you look at this analytical model, all the connection, important for me is if this connection part is well connected, so these node points are automatically connected. This is important for me to know. And now if I calculate now, this result will be, I mean, the calculation shouldn't have any problem, right? You know, you can see. And in SOFiSTiK is nice. You can check the warnings. If there's some warning that you can already check before sending to the calculation. And you know, the material mapping, load of nature, which is not here we have check. So you can also check if there is kinematic stability. If there is a problem, you can check before sending to the SSD. So if there is any error, for example here it has, I'm gonna show or let's say we can isolate. So here there is kinetic instability because of the structure here. So I don't know, we may check in this calculation, maybe it's not stable structure for now. Let's do the linear structure analysis, and the calculation goes, so it works, but I think pretty much I mean, this checking, it's only warning, it's not failure, so it still works. And if I do amplitude of 1, then this is actual deformation in real world. And if I do let me see the result in utilization, and if I look at here the double click on this mesh here, and the deformation, if you look here, is about, yeah, it's really small deformation you can experience. See, there is no deformation here in this case. Yeah, it's about like minus 0.003 millimeter and so on. So this is not a big deal. Alright, so that works perfect, and I'm gonna move on to next example. Now next example is about what if we change the profile of one side and the other side, and when you join them together, we have this sort of result. This is really not recommend joint modeling method for IFC workflow, because when you export IFC, you might have extra pillar below of this joint in IFC, but this is not a tema. I'm gonna explain IFC later in another video, but we are looking at more structural analysis. So this I'm gonna just export to SOFiSTiK calculation, and when you look now SSD, the mesh, for me the important thing is when you just looking at the static mesh, and if that mesh joint is correct, then for me this is the most important part. So looks good. So if I calculate again, we can see the dead road, and it's something that we expected, right? So we have here large force happening, and yeah, the deformed. Isn't it nice? It's really nice. Yeah. All right, next example. So next example is instead of changing the wall profile, we draw another wall. So it's just straight wall. There is no profile edited, and also another side here also, which is recommendable for me in more or less IFC geometry. To get correct IFC geometry, I recommend this solution. But nevertheless, in reality, we never model in this way, and also the reinforcement and etc. But I'm just curious. So we have like 4 different wall surface, analytical surface, which joined automatically. As you can see here, the green points, and I'm just going to see what result we get. Let me put the boundary condition on the other side here, and let's have a look. Probably this bounding condition, I'll make it to pin, and this family, let's change to pinned one, right? Let's go ahead with SOFiSTiK. I'm gonna calculate. Right, so the geometry comes correct. So as you can see, even though it's splitted, the joint mesh is clear to me, and they look really good to me. Now it's good to go for the linear analysis. I'm gonna calculate one more time. Linear analysis, and when you look at the dead road and deformed, the result is more or less same as previous example, as you can see. And what if I bring this result to Revit? Yeah, So let me go to show here. You see, even though it's physically split because analytical surface, they are linked each other, like it has a one sort of nice mesh geometry here. That's why we have like continuous result from SOFiSTiK, which is very nice. All right, I'm gonna move on to next example. And now we have here column, and this time the column, the column is joined with wall, so its wall goes wall is more primary structure, and then the column is joined. But nevertheless, you have here the analytical line of the column, and which is aligned with the analytical surface. And let's have a look what we get in this case. This case, the materials are mapped automatically, and section, if you look, this column size is mapped automatically to SOFiSTiK 30 by 45 centimeter, which is perfect. Now I'm just gonna calculate our dead rod and take a look in SOFiSTiK. So this is the analytical surface, and the mesh looks good for me. And when you look the cross section, it's gonna be look, because the column is, you see it's in the center. It's a little bit different than physical model because the column automatically aligned to the center from the center. And when you look at this model, it's gonna be look like this. But what is important for us is this static mesh. So if I now calculate the linear analysis, we have small warning there, but you can see the result. It's like that, so which is good. And in SOFiSTiK, because we have now framing structure, not only wall, so you can also see the support result. Of course, we can see, we can see the force or the moment of the support condition. And what I'll do, because we have column here, so I can also display our column result. So as you can see here, it shows the column result in Y direction. I'm gonna make it to Z direction, and you can see here the utilization of the column, which is really cool. And of course that the style we can change from here, or we can make the scaling of this result 40%, so not too big. And you can see this nice diagram from SOFiSTiK. This legend also we can bring it to here. So this is combination of wall and column, and it works perfectly for me in Revit and SOFiSTiK, which is very nice. I'm gonna move on to another, the same example, but this time wall is split at the joint with column, and column geometry is actually there, but the analytical model is same as the previous one. So as you can see, the analytical surface and framing is the same. It's just physically, what I did was on the modify, you have this join, and we can switch join order. When you switch the order, as you can see, the column is embedded in wall structure. And if I switch another direction, then you can see the wall is kind of splitted, divided, and the column is there. But the analytical model is the same, so the calculation result will be same. But nevertheless, we can go ahead and have a look the calculation. Right, and you can see here we have exactly same meshing, and when I calculate, you will get the same result. Alright, this is clear for me, so we can move on. Next one is actually we really split the wall between the column, and you can move with the wall end here, and the other end there. This case would be nice to compare the result with previous one. So we clearly have different analytical model. Let me calculate, and yeah, we'll leave it relative join tolerance. So let's calculate. It's curious. I'm curious because here, when you look at here in the static mesh, they are different. But when you give the cross section, it's maybe on the right hand side makes more sense because you have like column thickness, and at the same time wall is joining there, whereas the other is like they're kind of clashing each other. But static mesh on the left side looks correct for me, but SOFiSTiK, it seems like they do both calculation correctly. So let me do linear analysis of that. There is error. Yeah, instability check. So this node number 1004,563, and it's like it's not stable. So when I see, yeah, this column is moving around because it doesn't have support, you know. Yeah, it's clear for me. So in this case, in SOFiSTiK, what you can do, you can actually check, and you can click on kinematic instability. So when you check, there will be error, and it shows already these columns here. These are here. This column is not stable because we split the wall. This column doesn't have any more support condition. You can see. So now I'm going to give boundary condition for this column at point with a fixed condition. So now I'm going to calculate once more. Maybe for the comparison purpose, I'll also give the boundary condition at the column on here. So let's calculate now with SOFiSTiK. Start calculation, calculate. Alright, that's something we were expecting, and now I'm gonna do linear analysis. Yeah, the result is okay. So when you look at it, they are more or less same result, which is good. So I don't know which could be the best. Maybe structural engineers, you can leave the comments below. For me, it depends on situation, which maybe we can have a look next example because we have one more story above. But at the moment, with single level, the result looks to me more or less same. And let me bring this result back to Revit from SOFiSTiK. And if you look at the column diagram, bending moment, right? Yeah, here I see the column result, but on the other hand, the other model only showing the wall calculation result. It doesn't show columns structural result. So I guess on the left hand side it looks better to get the result here. Let me remove the column result for both sides. Support result. I want only see column result. Yeah, in this case here it shows. It doesn't show. It shows here. In that case, yeah. So it's interesting because when you see this column embedded between the wall, it shows all this result of shared force and, you know, the bending moment. But the other, you know, when it's separate here, it doesn't show the result. So, you know, that's also quite interesting for me. Alright, next example, I'll move on. The last example, I believe, here is same comparison. We have double story now. and the all analytical models are aligned correctly. Only here we have double story case. So let me calculate. Start calculate. Sorry about that. We have to put, of course, the support condition here, because this column is now not supported by anything. So let me here also provide another point support, nodal point, and let's calculate one more time with SOFiSTiK. And I'm curious now what result we'll get. Close, and let's go. So the mesh looks to me, yes, exactly, that's what we were expecting. And now if I calculate linear analysis, we get the result, and at the moment in SOFiSTiK they look both good, and I can also get all the utilization from this column here. Let's compare here. First one mesh here, we have minus 0.014 millimeter, and here so result is same. So if I go click on here, you can see that result or this result, they are kind of same. You can see they are exactly same result, and although they are split here or joined, when I bring back to Revit, just SOFiSTiK display, word display is all same, but when I do column result, you can only see the column result when a column is joined with the word's analytical surface. It doesn't show in this splitted word. So I guess left side is correct, more or less, better, and on the right side, because it doesn't show the result of the column in Revit, I believe it's not as good as the method on the left hand side. But I think, yeah, I really need your engineers' help here. Please leave me comments below what you think is the better performance, or in terms of reinforcement, or in terms of calculation result. I'm not engineer, so this part I'm lack of knowledge, but I would like to learn as well. So I would appreciate if you can leave the comments down below. So that's pretty much all at the end of the day. Let me summarize. So we looked at the whole structure here of the wall. So let me hide the legend. We looked at curved wall with opening and cut geometry of the wall end, and we looked at also with foundation with wall, and we looked at all joint wall connect condition, and also vertically and horizontally how we can manipulate the analytical surface of the wall. Looked at some cantilevered and cantilevered profile joined together. We looked at the splitted wall, which have the same situation as cantilevered profile here, and we looked at also joint condition between wall and columns. I'm gonna, just for fun, I'm gonna calculate all of this in SOFiSTiK. Calculate, and let's take a look at the result, and we can finish off today. Right, there was warning for more information. Alright, let's have a look in SOFiSTiK. At least we got all the, okay, support is too big. Let's make it smaller. Okay, we have here mesh density is denser because we changed the in SOFiSTiK property, but all the other looks as we expected, right? So let's calculate now the linear analysis of whole structure here. It will take more time, of course, because we have more elements, but it's relatively fast. Couple of seconds later, we got the result. Ooh, here, if you look at this word here, they have like much stronger behavior. I think it's because now SOFiSTiK sync as an entire project. You can see here the origin moved. So this sort of geometry here, it's funny. Let me make this to 50%, not actually more than that. So actually it's like the result is like we were thinking of, more or less, like, all good. This is we already expected. Alright, so let's move on Revit. I'm gonna display one more time the result of the wall and column. Let's go share force, and you see we have everything which we were expecting. Alright, I think that's all for today, and I think the part I wish to get some feedback from engineers, that this between the column and wall joint, I don't know which seconds or which minute of video exactly, but pretty much at the end. If you have some feedback for me, would be really nice to hear from engineers. And I don't know, we will look at the angled wall. As I said, we will have another prototype to look at the angled wall joint in the next video. And for today, it's more or less standard building wall joint part, and I think I demonstrate pretty much all the cases. Thank you very much for watching it today, and if you like the video, please like and subscribe my channel. That way you can support my channel to continue to produce some more videos in the future. And thank you very much for watching it. Bye bye.